Hello and welcome. This week in this video we're going to be doing baby's first circuit, right? So we're going to just dip our toes into the world of circuitry by talking about three main things. We're going to be talking about what a circuit is, what needs to be there to have some sort of functional circuit, and then two really important concepts of current and voltage. And then the work for this week is going to be mainly focused on a lab where we're going to be experimentally determining the relationship between current, resistance, and voltage, which is typically referred to as Ohm's law. So first, let's get started talking about what a circuit is. Alright, so to have a circuit, I need to have three things. The first thing is a power source. Right, and so my power source could be something as simple as a battery. We've got things called low voltage power supplies, which would be able to provide power to our system. Even the wall socket in your homes would qualify as a power source or power supply. So for this, we'll just look at the example of a little battery. Alright, so I've got a battery. Second, I need some sort of circuit element. I need to put something else into this circuit. So this can be a few different things. This could be, for example, a light bulb. This could be a capacitor, a parallel plate capacitor. Or what we're going to be talking about a little bit later today, something called a resistor. Right, and any of these circuit elements or some combination of them we can put into our circuit in order to make it do things, like for example light up a light bulb. So in my little diagram over here I'm going to put my light bulb, and then last I need wire, which is connecting everything in a complete loop. Alright, so what that means is that I need wire that's connecting both terminals of my battery, the positive and negative ends of my battery, along with connecting it to whatever circuit element is in my circuit. So in this case I've got a light bulb, so I can just draw in some wire that's going to be connecting the positive terminal to the negative terminal. And since it's forming this complete loop, that's going to allow current to flow through my loop and the result is that my light bulb in this case is going to light up. Alright, so once we've got this completed circuit, there are a couple things that we can introduce to help us analyze what's happening mathematically, right? Start applying some physical laws to understand the circuit and what it's doing. And the first of these concepts is going to be current. Alright, so when I was talking about the two terminals of the battery needing to be connected so that the charge is going to be flowing, that flowing charge is what we're going to refer to as current. So I can say that the current is the rate at which charges are moving through, moving past a particular point in the wire. Alright, so if I want to write down the equation for this, if it's a rate, that means that it's how is it changing with respect to time. So my equation for current is going to be the change in charge, right? The amount of charge that's going past this particular point in a particular amount of time. Alright, so if I'm looking at a close-up, little cutaway of my wire, I'm going to have a bunch of charges that are free to move around in this wire, and kind of bouncing around inside, but are generally moving in a particular direction. Right, and this is my current. And I'm looking for how many of these charges are moving past this point in a particular time. And if I want to be a little bit more specific about that, I'm talking about a particular cross-sectional area. And so there's a area that we can draw in to my wire. All right, and so that's the point location on my wire, and we're saying how many charges are going through that area in a particular amount of time. Right, so the more charges that are going through, right, the larger the current, or if they're moving quickly, right, maybe I don't have as many charges, but a lot of them are getting through in a particular amount of time, I'm going to have a larger current. Right, there is the analogy that I note in the summary for this week on the analogy to water, right? So if I have water that's moving in a stream, right, we've got a water current that we can talk about, like a riptide, right, or strong currents in a river. We're doing the same thing with that type of water current as we are with an electrical current, which is that a strong water current means that I've got a lot of water, right, a lot of water molecules, and it's moving very quickly, right, that would produce a strong current. And so the same thing is being said about the electrical current, it's just that we've got a lot of charges and they're moving relatively quickly. All right, and then the thing that I forgot to write down is that this variable I, that's not what I want. So variable I is the variable for the electrical current, because that makes sense. And the units for this are amperes, often referred to as amps, and is symbolized with a capital A. The second main topic that we want to look at is resistance. Right, and we're looking at the situation where if I just take a battery and I connect the two ends of it with a piece of a wire or like a gum wrapper, I'm basically just going to drain that battery. The charge that's being stored on it is going to move through it very quickly, and we're going to lose power from that battery. And part of the reason that it's moving so quickly, if it has a large current, right, is because there's nothing slowing them down in the very good conductor of a metal. So one of the things we can introduce, or one of the things we often introduce into our circuits, is something to slow the charges down. Again, in the analogy with water, if I've got two pipes, right, when the diameter of my pipe decreases, right, that's increasing the resistance to the flow of the water. It's going to be harder for that water to get through that smaller pipe. And so we're, right, again, adding resistance to the flow of the water. And so one of the circuit elements that we can add into our circuit is something called a resistor. And resistors are going to do that same thing. They're just going to slow down the flow of the charges in that circuit. All right, so how do we slow down the flow of charges? Well, as I mentioned, wire is a very good conductor, and so essentially we're just introducing something that is not quite as good of a conductor. A lot of resistors, and I guess I'll write this down, a lot of resistors, which is one of these circuit elements, are made of ceramic. And while some ceramics can be considered conductors, they're certainly not going to be as good of conductors as metal is. And so it's going to have the effect of slowing the movement of the charges through the circuit. All right, so resistors have this quantity of resistance associated with them, and the resistance depends on the material that the resistor is made of and the geometric properties of the resistor. And when we're measuring resistance, this is going to be measured with units of ohms. And a typical resistor is constructed to have a resistance from anywhere from about 2 ohms to maybe 10 mega ohms, or 10 to the 6 10 times 10 to the 6th ohms. Those are some typical values for resistors. So again, we construct resistors to have a particular resistance. It's not something that depends on what type of battery that you have, or how much current is flowing, or what other resistors are in your circuit. It just depends on how it's been manufactured. All right, so for the second part of this, we're going to collect some data that you will then be asked to analyze as a part of your homework for this week. And we're going to collect that data using this FET simulation, so circuit construction kit, which there's a link provided to. I'm going to go to the lab option. And on the left-hand side of the screen, I've got a bunch of different circuit elements: batteries, wire, light bulbs, a resistor, switches, so many more, all the way up to and including a dog, right, that I can put into my circuit. Not something that I've typically list in the circuit elements. And then on the other side, I've got the ability to show the current. This electrons versus conventional is because Benjamin Franklin, who was first writing about current, had to make a choice about the direction that the current was flowing. Basically this way for positive charges if it's positive charges that are moving, and this way if it's negative charges that are moving. And so he assumed that it was positive charges that were moving and defined the current to be flowing in that direction. Turns out it's actually electrons that are moving, so the convention is in one direction and the actual movement of the charges is in the other. And we just never fixed it. So we'll be looking at the electrons. We've got a voltmeter, which is going to be able to tell us the voltage between any 2 points, the change in voltage between any 2 points in our circuit, and then an ammeter, which is going to measure the current. We can also change the wire resistivity. Wires we tend to assume that they don't have any resistance at all, when in fact they do have some, but it's a tiny amount, so I'm going to leave that there. And then the same thing for batteries. Batteries have some sort of resistance that's associated with them in an actual situation, but we're going to just leave that as 0 and assume an ideal battery. Okay, so for this lab, I'm just going to construct a simple circuit where I've got a battery, a resistor, and I'm going to connect these together with wire with an ammeter so that I can see what the current is. Right, and then we're going to collect data on this, right? What is the current that we're reading for the different voltages coming out of the battery, and we're going to assume that the resistance, or we're going to set the resistance to be 100 ohms. All right, so we'll do that first. My resistance, I want to be 100 ohms. And you can see the bands on the resistor changing depending on what resistance I have. So we get to 100, brown, black, brown, 1, 0 times 10 to the 2 for the resistance of my resistor. And that's just going to be a fixed value. That's going to stay exactly as it is. First, what we can do is we can say, all right, if I've got 0 volts from my battery, what is the current in my circuit? And the current is 0, so that'll be a first data point. All right, we had 0 volts, and my current was 0. All right, so then let's go up to, let's do 5 volts. All right, with 5 volts, I've got 0.05 amps. All right, let's do another, about 10. 10 volts, I've got 0.1 amps. and I'll just keep doing this for the rest of the trials. Alright, so a couple things to notice. As we're bumping up the voltage, we can actually see the electrons in the wire that are moving faster or slower, right, in association with my current getting smaller or larger. The other thing that I'd like to point out is that in Excel, I need these to just be numbers, right? So my units I'm putting up in the heading, right, not along with the number. And I can tell that I've done it correctly because the number is showing up on the right-hand side of the cell, unlike up here where I'm marking off my resistance. I put it in with the unit, and so it's showing up on the left-hand side. Alright, so what I'm asking you to do is to create a trend line of this data. And so I'm going to go down here to another page to remind us how to do it. You should have that page that's walking you through these steps, but I'll just do it one more time for you. Alright, so I'm going to do this from the bare minimum, which means I'm just going to start by saying insert chart. And so it will produce a chart. And I want this to not be a line chart, but I want it to be a scatter. So it's showing up in the suggested for me, but I can also scroll down and I can see the scatter chart right here. All right, and it's also kind of pre-populating this with some data for me, which is really nice, but not useful if it doesn't do that for you or it doesn't do it correctly. So I'm just going to get rid of that data so we can do it again. Okay, so add the x-axis, right? So in this case, I want my x-axis to be my x data. So I need to select a data range. So I've highlighted this. I'm going to go over to x, and I'm going to highlight the data by holding down Shift, or you can use your mouse to just drag that down. And I got A3 through A13, and that's correct. Okay, except that it's using the first row as a header, which I don't want. There we go. Okay. And then I'm going to add this series, which is the y-axis. I'm going to do the same thing. I'm going to highlight this. I'm going to go over to the y. I'm going to highlight 3 through 13, hit OK, and it's filled in with my data, all right, which is showing up. Now, if I'm actually looking at this data, you should probably get a pretty good sense of what it is, right? I've just put in 0 through 10 and 0 through 10 on both. So I'm expecting this to create a y equals x graph, but we can actually see that because it doesn't necessarily have to be perfect, or the data isn't necessarily perfect. So down in my series tab, all right, so chart editor, customize series, I'm going to scroll down, I'm going to hit trend line. I want it to be linear, and I'm going to label it with my equation, and I want to include the r-squared, which is a measure of how closely the points are to my line. All right, and once I've done that, then my graph is showing up right here. All right, so y equals 1 times x plus 0 with an r-squared of 1. So it's perfect. It's a perfect fit because my data is perfect. Note that this is going to show up as x no matter what data you put on your x-axis. Right? So if I change this to something else like distance, right, and this is my voltage, right, this is still going to show up as 1 times x, right, and I'd have to put in the fact that this is actually telling me that the voltage is equal to 1 times the distance, which would mean we've got an electric field of 1 Newton per Coulomb. Ugh, what did I do? All right, the other way that you might be able to get away with getting the chart in there is just to highlight all of the data, as long as you've got your x column or your x data first and your y data second, and you can just do insert chart. And sometimes it just does it for you, but again, you can also just manually select the data for the x-axis. And then one more time, customize up at the top, series, trend line, label, use equation. All right, and that's going to give me my trend line equation, show r squared. All right, and so that is how you do that. All right, so I think that's it for this video. Let me know if there are any questions, and good luck out there.